We're going to see how to make sodium chloride in the lab. And we're going to start from its elements, from sodium and from chlorine. And the first thing we have to look at is how to do it safely. So wearing goggles, gloves, an apron, lab coat, and do the experiment in a working fume hood. And do not remove the chlorine or the apparatus until it's fully empty. Chlorine is a poisonous gas, and only a qualified chemistry teacher should be doing this experiment, including cutting and heating the sodium. So as the first activity, write the equation. You've got the word equation here, so write a balanced equation with symbols and formulas, and pause the video while you do this. And the reaction needs a little help. So the activation energy will be achieved by heating the sodium and indeed melting it, because it's got a relatively low melting point. To start with, we're going to make the chlorine, and here we have a gas generator with a tap funnel and then a flask which will contain potassium manganate 7, potassium permanganate, and it has an exit tube, the delivery tube, which goes into a gas jar. And how you collect the gas depends on the properties of the gas that you're collecting. And here the chlorine is soluble in water, denser than air, doesn't react with air, so it's collected by upward displacement of air. So the delivery tube goes right down to the bottom of the gas jar to deliver chlorine that is made. And how do we know when we've got enough chlorine in it? You can see chlorine, but you can also test for it with some damp universal indicator paper just put at the top of the gas jar. And it's first orangey yellow and then may go pink because a solution of chlorine is acidic, but the chlorine will very rapidly bleach the indicator paper. So when you've collected your gas jar, lift the gas generator delivery tube and tube out and put a lid across it until you're ready to react with the sodium. But just before we prepare the sodium, write the equation for the preparation of chlorine, here from potassium manganate 7 and concentrated hydrochloric acid. You've got the word equation there, and so pause the video while you finish the equation, and you've been given the reactants and indeed the reacting coefficients. So here's the equipment needed to prepare the sodium for the reaction. All of it normal. The one that may be different is a deflagrating spoon, a small spoon, probably just a centimetre and a half in diameter, with a long wire handle, and as we use it, there'll be a disc around it to act as a gas jar lid. That's the deflagrating spoon. But you're going to get the sodium out of its container, and with tongs put it on some paper towel on a white tile, and you then are going to fold the paper towel over to dab off the oil which covers the sodium when it's in the jar. And because it's sodium, it's easy to cut, so you can do it with a spatula. And you want a pea-sized portion that you're going to use in the experiment, and put the rest back in the jar. Make sure it's under the oil so it's not going to react with the air, and screw the lid on tightly. So you're going to put that small fragment in the deflagrating spoon, and there is that little lightweight metal disc, which will be the gas jar lid. And you're going to just lift it into a Bunsen flame and heat it gently for about 20 seconds. And you may see a tiny flame, and that's because the heat energy provides energy for electrons to rise to higher energy levels, and you'll see a color as they fall back down to the ground state. And here it says is the formation of the flame that you see, an absorption spectrum or an emission spectrum. So you can pause while you consider that one. And then once it's melted and formed a little sphere, you don't want to react it with the air for too long. So I say about 20 seconds in all, and then carefully carry it to the fume hood where your gas jar of chlorine is. Take the lid off, put the deflagrating spoon with the molten sodium down into the gas jar, and make sure that it doesn't touch the glass side of the gas jar, and describe what you see. And once it's cooled down, you can look more closely at it. You've seen in the video which part is the product. Too much sodium oxide on the outside, and then I just plunge it into here. That's somewhat slower than I'd like, but it's okay. It's actually making salt. Okay. And then at the end of the experiment, go back and clear up where you've been cutting the sodium. Put everything into a beaker of water so that any fragments of sodium will react, and that includes the paper towel, because it'll be a fire risk if you dispose of it. And then we have a few questions to look at the theory of the sodium chloride. And so what's the bonding? So we're looking at the elements sodium and chlorine on a periodic table, and see that sodium's in group 1 and it's an alkali metal, and emphasize the metal, Chlorine in group 17 is a halogen, and it is a non-metal. And so when they react together, they're going to form an ionic bond. The single electron in the outer valence shell of sodium is donated to the outer valence shell of chlorine, and it fills it, and chlorine now has an octet. So the sodium becomes an Na plus ion, and the chlorine atom now becomes a chloride Cl minus ion. And you see the structure below, which we will look at in a little bit more detail. When you see salt crystals, and you can look at table salt with a magnifying glass, you see that they're cubic. And then if you look at the diagram on the right with alternating large green chloride ions and purple sodium ions, they fit together in a cubic structure. And something for you to consider, lithium has a smaller ionic radius than sodium in lithium chloride, and potassium ions in potassium chloride have a larger ionic radius than sodium. How do you think that will affect the shapes of the lithium chloride and potassium chloride crystals? So pause while you consider that and say why you think they'll be the same or different, and then research the shapes to check your answer. And then whilst we're looking at sodium and sodium ions and chloride ions in a lattice, each grey sodium ion is surrounded by 6 chloride ions, and each of the 6 chloride ions is surrounded by 6 sodium ions, and we say they have 6-6 coordination. Then we'll look at some of the uses of sodium chloride, and it's a medication for intravenous drips in Ringer's lactate, and so for emergency use to include blood pressure or restore electrolytes, it's a specific concentration of salt with sodium lactate, potassium chloride, and calcium chloride. It's in a fire extinguisher to extinguish metal fires, so a D-type. Don't put water on metal fires. In water softeners to remove insoluble calcium ions, in drilling fluids around the drill head in oil and gas exploration, to salt out contaminants in textile dyeing so that the actual dye is what is captured by the textile, used in making wood pulp in the paper industry as it bleaches wood, and has been used a lot in the past for food preservation. Salt is a desiccant, removes water from foodstuffs, and as it dries it, makes it suitable for long-term storage. And it's used in the extraction of the metals that are listed there. And finally, how does a salt crystal dissolve? So I've got a beaker there with some salt in it at the bottom and the water above it. Water is polar, and the delta minus of the oxygen atom in water is attracted towards the sodium ion in the salt crystal. But remember, water particles are going to be moving, and so that jostling of the outer layers with the oxygen attracted dipole to ion attraction, and ditto with the delta positive on a hydrogen atom in water and the chloride ion, is what is going to cause the solution. And then we say thank you to Washington International School, Team Science, and their IB chemistry student.